All right, welcome back. So we'll get started with the second talk of today's afternoon session. We have Lise Wouters, who's going to tell us about equivariant Jiang-Su stability and equivariant property gamma.
Yes, thank you. This is working, right? Okay. Yeah, thanks first of all for the organizers for inviting me. I will indeed speak on equivariant set stability and equivariant property gamma. And Hannes was indeed right today. A will always stay a C-star algebra. And moreover, throughout this talk, I will work with actions of countable discrete groups. And the C-star algebras will always be assumed unital and separable. We have results beyond the unital case, but this is just for simplicity of the talk. And I will be assuming that there are tracial states around. This is all joint work with my supervisor, Gabor Sabo, by the way. And so when these tracial states are around, we get seminorms from them. So here we get the tracial 2 seminorm like this. And then we get a uniform norm or seminorm where we take the supremum over all the traces. And for example, in the simple case, these will be norms. You will probably hear me calling them norms when they might not be, but in general, they're just seminorms. And let's start with, first one more remark. So if you have the tracial 2 norm from some tracial states, then you can look at the GNS representation related to that trace, take the weak closure, and then this tracial 2 norm induces the strong operator topology on this von Neumann algebra. So these norms have some von Neumann algebraic character. And so now let's start with the big picture of the talk today. So if you have this in mind, I wrote it on the blackboard so you can keep looking at it throughout the whole talk. So basically, the whole point of the talk is whenever we have an action and we have some local information with respect to one tracial 2 norm or seminorm at a time, I will be more precise about this later. How can we go to a global uniform tracial information with respect to the uniform tracial 2 norm? And by this information, I mean like certain statements or properties or estimates that are almost satisfied, or that certain approximations that almost hold with respect to this norm or with respect to these norms. And so where do the two things in the title of this talk apply? So first of all, as I said, these tracial 2 norms, they have some link with the von Neumann algebra. So this here on the left side, we will always use our von Neumann algebraic knowledge, things that we know from the theory of von Neumann algebras. And while on the right side, this information with respect to the uniform tracial 2 norm is something that we can deduce, something that sometimes holds interesting properties of the C-star algebra. And one example that we will consider in this talk is equivariant set stability. And then equivariant property gamma, as we will show, turns out to be a tool to go from the left side to the right side. So this is the tool, and this is the example that I will come back to during the talk. So with this in mind, I'm going to start by introducing the example or giving some context there, like why we should be interested in that. And this has to do with classification. So first, let's look at the ordinary classification. So for von Neumann algebras, these were classified in the 70s by Kohn and Heurup, or at least they classified the separably acting injective factors. And one important or object that I want to draw attention to is the hyperfinite to one factor. So this is like the infinite tensor product of matrix algebras that you can represent by looking at this as a unique trace and then representing this by the GNS representation with respect to this trace and taking the weak closure, we get a von Neumann algebra. This is the hyperfinite to one factor. And so in this classification, Kohn in his annals paper showed an important thing, namely, first of all, every injective to one factor absorbs tensorially the hyperfinite to one factor. And this was then used to prove that the hyperfinite to one factor is the unique injective to one factor. So injectivity and hyperfiniteness are equivalent. And so this tensorial absorption is used in the proof. Now, on the C-star algebraic side, the original goal of the Elliott program was to try to see how far we could go and mimic this classification of the von Neumann algebras by putting here the analogous adjectives, so separable, nuclear, simple C-star algebras. And the goal was to classify these by a manageable functorial invariant. There were some positive results for inductive limits and so. And this led to the early conjecture that these could be classified by what is called the Elliott invariant. And it's not that important to know all the details. There's some K-theoretic part that I will not really use too much. The tracial states are there, and there's some pairing between the two. And so this was the initial hope. But then it turned out by examples, for example, by Toms, that there are some exotic examples that, well, if you take these C-star algebras A's, which are inductive limits of these forms, so the building blocks are comparably easy, but the dimensions of these spaces, these Xn are Hausdorff spaces, locally compact Hausdorff spaces. They grow fast compared to the dimension of the matrix algebras, and they are not isomorphic to their tensor products with the Carr algebra, but yet they cannot be distinguished by the Elliott invariants. And even more, they can also not be distinguished by other, what I call nice invariants, and Toms makes this precise in his paper. So by this I mean like easy enough to work with, or easily enough computable in examples. Because you could, for example, look at a Kuhn semigroup and then you could distinguish them, but then this is not so manageable anymore. And this then led to a shift in focus to instead try to determine maybe the right regularity criterion to restrict these examples and restrict the scope of the classification to get to a classification by the Elliott invariant. And one of these possible regularity criterions is set stability. So Jiang and Su in '95, they showed that there exists a unital, separable, simple, nuclear C-star algebra that has the same Elliott invariant as the complex numbers, but yet it's infinite dimensional, so they're not the same. And moreover, under some mild condition on a C-star algebra A, the Elliott invariant also behaves well with respect to taking tensor products. So then the Elliott invariant of a C-star algebra A will be the same as the Elliott invariant of A tensor C, and will then be the same as the Elliott invariant of A tensor the Jiang-Su algebra. And this means that the Elliott invariant can never distinguish a C-star algebra from its tensor product with the Jiang-Su algebra. So the only C-star algebras that we can hope to classify by the Elliott invariant are the Z-stable C-star algebras, so the ones that are already isomorphic by the Elliott invariant. And so this is like a necessary condition for classification somehow. And then by the combined work of many people, this is also sufficient, more or less. So if you have, oh, what's happening? If you have two unital simple separable nuclear C-star algebras that are Z-stable and satisfy some technical condition, the UCT, then they are isomorphic if and only if their Elliott invariants are the same. And there are other possible regularity criterions that you can put here. Then you get the Thomson-Winter conjecture, which predicts that they are equivalent in the right setting, and several implications have been proved. There's one implication open, but I won't go into this too much now. Okay, so this is the setting without actions. Now, if we put actions into the picture, then first of all, we're interested in classifying these actions on unital C-star algebras up to co-cycle conjugacy. So let me quickly remind you of the definition. This means that there exists a star isomorphism between the algebras that like almost intertwines the actions, but there is an additional map, the co-cycle, satisfying this co-cycle condition. So we allow that there is that we might conjugate by some unitaries. And this is actually necessary, this added flexibility of the unitaries, because otherwise the classification would be too hard. It would be unfeasible. So this is why we added there. And so now again, the goal is, okay, now that we have a classification for the C-star algebras, can we classify their symmetries, so their actions, up to co-cycle conjugacy. But again, there's like a similar problem that occurs if you take an action on a C-star algebra, and then you take the action on its tensor product with the Jiang-Su algebra, where you act trivially on the second factor, then again, a nice enough invariant will not be able to distinguish the two. And this is again like computable enough or something. So again, our best hope is to only, well, we cannot hope to do more than classify the equivariantly Z-stable actions. So the ones that are already co-cycle conjugate to this tensor product action. And this gives us two questions if we're interested in the potential scope of classification, because this is again some necessary condition. We can ask ourselves, okay, if we have actions of countable amenable groups on these C-star algebras that we could classify already, when are these actions equivariantly Z-stable? And actually, could this be automatic in this setting and follow from the Z-stability of the C-star algebra? Because right now we don't have any counterexamples to this. We have only evidence showing that this is indeed true in some cases, but we don't have the full result. And a second question is, okay, if we then have equivariant Z-stability for actions, which other structural consequences might this have? Because we now know that if we are going to attempt some classification of the actions, we will definitely, they will have to have this property. So maybe this property might have some other nice consequences that we can then use in classification or tell us something about this. Okay. So this is an introduction to this, this question or this problem. Some remarks. So I rephrased this a bit more imprecisely. So we're interested in which actions are equivariantly Z-stable. And the reason why I put amenable in front of the group is For non-amenable groups, there are counterexamples. So if you look at the action of a discrete group G on the infinite tensor product of the Jiang-Su algebra just by permuting the factors, then this action is equivariantly Z-stable if and only if the group is amenable. So this question cannot in general be true for amenable groups. Maybe you could try to do something for amenability on the actions, but I don't want to go into that. Another remark is that, again, the analogous question has a positive answer for von Neumann algebras. So if you take some action on an injective type 2-1 von Neumann algebra by a countable amenable group, then this will be co-cycle conjugates to its tensor products with the trivial action on the hyperfinite 2-1 factor. So here again, this hyperfinite 2-1 factor plays the role of the Jiang-Su algebra in the C-star algebra case. And this is for the factor, when M is a factor, this follows from the work of Ogniano, and then more general, this is Sutherland Takasaki. And then one last remark is that if there are no traces around, then we already have the full positive answer, because then by some equivariant Kirchberg-Phillips type result of Szabo, he showed that any action of a countable discrete amenable group on a Kirchberg algebra, which are precisely the C-star algebras in the classification theorem that do not admit traces, they actually automatically absorb the trivial action on the infinite Kunz algebra, and this action then absorbs the trivial action on the Jiang-Su algebra. So this implies the Z stability. Okay, so this was the introduction to the problem. Now, why did I put it on this side of the blackboard? This is because equivariant Z stability in this classifiable setting can be reduced to a tracial problem. So whenever we have an action of a discrete amenable group on some unital separable simple nuclear Z-stable C-star algebra, then this is an argument that goes back to Matui and Sato, and it shows that, or it establishes an equivalence between the action being equivariantly Z-stable and the existence of approximate star homomorphisms from matrix algebras into A that are approximately unital, central, and fixed under the action with respect to this uniform tracial 2 norm. Now, this might be a bit confusing, so I actually wrote this out a bit better, but this might be a bit technical. I don't know. It's whatever you prefer. So basically what I mean by this, for every epsilon error that you tolerate, for every finite set in your group and in your algebra, you can find these elements which will act as the images of the canonical matrix units in your matrix algebra that are satisfy like almost the properties of the matrix units in the algebra. And this condition here will see to that the image or the sum of the images is almost the unit. This will say that they almost commute with this finite set of elements that we chose in our C-star algebra, and this will say that they are approximately fixed under the action. And all these approximations are with respect to the uniform tracial 2 norm. And so let me actually write this here. So all of these things here, these estimates, are examples of so-called G-star polynomials. No, what? G-star polynomials. And so basically, what are these? These are polynomials where we have some variables and we are allowed to put like the action in there, and we're allowed to put stars in there. So These some so oops, spoilers. Now this can go up. Can it go further up? Yeah. Okay, so we have these the set of star polynomials, and basically what we're asking for here through this equivalence is elements in the C-star algebra that when you plug them into these polynomials, or at least a finite set at a time, the uniform tracial 2 norm becomes very small or arbitrarily small. And then this is the right side of the picture, but on the left side, if you look at the analogous thing for von Neumann algebras, so if you look at actions there that are co-cycle conjugate to the trivial, to their tensor product with the trivial action on the hyperfinite to 1 factor, then again, this means that we can find these approximate star homomorphisms into the von Neumann algebra, this time where all the estimates hold with respect to the tracial 2 norm coming from this, the trace of the von Neumann algebra. And so this is how we will use this side, because as I told you in the previous slide, the analogous question for von Neumann algebras had a positive answer. So basically, if we can somehow use this von Neumann algebraic knowledge and then make these solutions into some uniform tracial solutions, then we are in business and we have our equivariant set stability through this equivalence. So let me draw a picture. Suppose these are the traces in your C-star algebra. Then basically the left side means that for each point in your tracial simplex, you have some solutions. But then if you put like the weak star topology on the traces, there will always be some small environments where these same solutions also are still approximate solutions. And then basically compactness of the tracial state simplex would allow you to reduce this to some finite set of environments. And basically you want to somehow glue these together to some uniform solution that works on the whole tracial state space. Okay. So a quick intermezzo on these tracial state spaces. So whenever we're working with a unital separable C-star algebra, the tracial states form what is called a Choquet simplex. And this is a compact, convex, metrizable subset of some locally convex space, a bit technical, such that each point is represented by a unique probability measure on the extreme points of the simplex. It's not really important that you remember this precise definition, but there is some variety in Choquet simplexes that can occur. So first we have the quite tame ones, which are the Bauer simplexes, where the extremal boundary is compact. And in this case, these are just isomorphic to the compact spaces with their probability measures on them, because exactly in the definition of a Choquet simplex, the probability measures, each point is represented by a unique probability measure. But then you have also more exotic simplices, such as the Paulson simplex, and this is something weird where the extreme points of the simplex are dense in the whole simplex. So then the structure becomes way weirder, and you can imagine that these type of gluing arguments really depend on how complicated the tracial state simplex is. And moreover, this is something that we cannot ignore, because there's this range result by Blackadder that shows that any metrizable Choquet simplex really arises as the tracial state space of some unital simple AF algebra. So also quite simple C-star algebras even. And then whenever you have an action on a C-star algebra, this induces an action on your tracial state space by this formula, and this restricts to an action on the extremal tracial states. And you can actually show by some simple arguments, well, not necessarily simple, but an argument relying on some classification theory, that any affine homeomorphism on a Choquet simplex, for example, is induced by an automorphism on a classifiable C-star algebra. So I have written out the argument here, but let's skip it for now. And basically, so this means that really we should worry about these difficult, possibly complicated structures. So this then brings us to property gamma and this gluing trick that I will explain now. And for this, I will first give some definitions. So instead of working with these approximations, it's often easier to work with ultra powers, where all our estimates become exact. So we define the uniform tracial ultra power like this. We mod out by the sequences that go to 0 in the uniform tracial 2 norm. And then our own C-star algebra A embeds canonically into this as the constant sequences. So we can look at the commutant and consider the uniform tracial central sequence algebra. Our action extends to an action on this uniform tracial central sequence algebra. And each sequence of tracial states defines a new tracial state on this uniform tracial central sequence algebra by just sending a sequence along to the limit from this sequence of traces applied to the sequences. And this set will denote the set of all limit traces. And for example, with this notation, now these approximate statements that I gave become an exact statement. And we can say that under all these assumptions, as an action is equivariantly Z-stable if and only if there exist unital star homomorphisms from the matrices into this fixed point algebra of the uniform tracial central sequence algebra. And for example, when A has a unique trace, then when you look at the GNS representation and take the weak closure, this will become a finite factor. And by Kaplanski's density theorem, this uniform tracial central sequence algebra is actually isomorphic to the tracial central sequence algebra that you know from von Neumann algebras. So in this case, you take the sequences, bounded sequences, and mod out by the sequences that go to 0 with respect to this one tracial state of the von Neumann algebra. And then in general, but maybe I will go a bit quicker over this, you can define some uniform tracial closure. And this fits in this upcoming framework of tracially complete C-star algebras that is coming. And you can also get an isomorphism here, but I will skip this for now. Okay, so now let's come to the definition of our other main property that was in the title. Or first, the non-dynamical version of this, which was introduced by Jorge Castillejos, Sam Evington, who's here, Arend de Quissis, Stuart White, and Willem Winter. And so this is actually based on the von Neumann algebraic version of this property, which was already used by Murray and von Neumann. And they defined for a unital separable C-star algebra with a non-empty set of tracial states, that it has uniform property gamma if and only if you can find some projections in the tracial central sequence algebra such that they sum to 1, which means they automatically have to be orthogonal, and such that they cut these limit traces, they divide them by n, 1 over n. So this is a bit technical maybe, but the theorem they showed, so these people, they proved some equivalences. So under these assumptions, they proved that a C-star algebra has uniform property gamma. Then this implied some property called complemented partitions of unity, and I will not give the definition here, but somehow this is like the right tool to do the gluing here. And then with this tool, they can then show that this is equivalent to the existence of unital embeddings of matrix algebras into the tracial central sequence algebra, which is of course the non-dynamical version of this criterion I established. So, and then this third condition implies the first, because you can, for these projections in the uniform property gamma, look at the images of the standard projections alongside the rank 1 projections alongside the diagonal, because they will specifically satisfy this tracial cutting property because of the uniqueness of the trace on matrix algebra. And so equivariant property gamma is a dynamical generalization of this, which was introduced in the work of Eusebio Gardella and Ilan Hirschberg and Andrea Vaccaro. And just the only thing that changes is that you ask for the projections not to be in the central sequence algebra, but in the fixed point algebra of the tracial central sequence algebra. And a first remark is that this property is clearly implied by equivariant Z stability. Why is this? Suppose that we have an equivariant Z stable action. Then we have some co-cycle conjugacy, so some isomorphism between A and A tensor Z that behaves well with respect to the action, apart from some co-cycle like this. And actually, this induces a star isomorphism between these central sequence algebras. Now, maybe if the co-cycle wasn't there, you would see this immediately. But when the co-cycle is there, it doesn't really matter, because you're actually conjugating when you apply this map pointwise to a sequence, the co-cycle will then be conjugating by a constant sequence of elements, and we're working with central sequence algebra, so these commute and it doesn't matter. So we get a star isomorphism. So it suffices to find these projections in tracial central sequence algebra of the Jiang-Su algebra, because this unitarily embeds inside this one. And then this you can do because the weak closure of the Jiang-Su algebra with respect to the GNS representation with respect to its unique trace is a hyperfinite to 1 factor, and there we can always find these projections. Okay, so now I'm going to talk how this, I'm going to state a consequence of this equivariant property gamma, namely that it leads to some kind of local to global principle that allows one to go from these solutions 1 trace at a time to the global things. And for this, I alluded to this in the beginning, that these tracial 2 norms, they have something to do with these von Neumann algebras. But of course, when we're working with actions, we need to have some equivariant representation so that the action nicely extends there, so that we can actually from our original C-star algebra, build some von Neumann algebra where we can then deduce the properties and then use our tools to go. So for each trace, we have the GNS representation, but then we make it equivariant by letting it act on, well, the direct sum of G copies of this Hilbert space in this way. And then we can take the weak closure of that von Neumann algebra, which will live inside of here. And then the resulting strong operator topology will be induced by the tracial, the translates with respect to the actions of this one trace that we picked in the beginning. And more importantly, the induced action on this image is implemented by the left regular representation. And so we get an induced action on this reclosure. And so basically what the tracial local to global principle tells us, I should mention that prior results have been obtained by these three people that I just mentioned in case that the action induced on, it should just be the tracial states here, has finite orbits uniformly bounded in size. So then I showed together with Gabor Szabo that suppose you have an action of a countable discrete immutable group on a unital separable C-star algebra that has equivariant property gamma, then basically you can go from these solutions one trace at a time to the solutions in the uniform tracial two-norm. So if you have some countable set of sequence, some countable set of G-star polynomials, and suppose that for every epsilon tolerance and every finite subset and for every tracial state, you can find approximate solutions in this reclosure of this representation that I just defined, then you can actually find contractions, or you can do the same for the uniform tracial two-norm, but then you can rewrite this in a nice way with the uniform tracial ultra power where the statement becomes exact and you can find exact solutions in the ultra power. And so here, okay, we might not have a countable set of equations, but if you reduce to a dense subset of A, this is a countable set of equations and this applies. And this might be a nice way of stating it, but or maybe insightful with the polynomials, but if you want maybe a more, I don't know, elegant way to state it, another way to see it or to phrase this principle is the following. So suppose we have some separable subalgebra of some other separable algebra D with an action delta. And suppose this smaller algebra embeds into our C-star algebra with the action that has equivariant property gamma. Then this, of course, is included into this uniform tracial ultra power. Now then we can ask for this map, this psi, to extend to a map from all of D. And the principle says that you can do this if and only if you actually have another map here. All right. If you can do this again, one trace at a time, where you not look at the whole uniform tracial ultra power, but the tracial ultra powers, of these representations. So it's equivalent to trying to extend it to this ultra power and being able to do it for each trace separately for the other ultra power. And the link between these two is that you can think of, well, the statement says you can do this for any inclusion. So basically you work with some kind of universal C-star algebra encoding the relations that you have over there. And so with this, in this way, you can also nicely see, maybe you're already convinced by the G-star polynomials by now, but you can also nicely see that we indeed get these embeddings of the matrix algebras, because how can you translate this instead of finding a matrix, an embedding of the matrix algebra? So basically, in this case, RB will be our C-star algebra A, and this will be the canonical inclusion, and this will be Mn tensor A. And then doing this, because of course the tensor product, the two factors commute, will actually, this is equivalent to finding this unital star homomorphism there. So by the tracer local to global, it's enough to do this one trace at a time. If you then decode it again, you want to find these embeddings of matrix algebras into this central sequence algebra of this von Neumann algebra here. And this is true precisely because here we have an action on an injective type 2-1 von Neumann algebra, which absorbs the trivial action on the hyperfinite 1 factor by, again, this result I mentioned of Opniani and Sutherland Takazaki. And as a corollary, we get that actions of countable discrete immutable groups on unital separable simple nuclear stable C-star algebras have equivariant Z stability if and only if they have equivariant property gamma. And so now we have these two equivalent properties, so we can rephrase the question that I asked at the beginning, like which actions, or do all actions of amenable countable discrete groups on these unital separable simple nuclear Z stable C-star algebras have equivariant property gamma? It's not that this, right now, the property gamma has not led to any more examples that were not already known beforehand through more direct techniques. But more importantly is also because Z stability implies equivariant property gamma, this gluing technique or this tracer local to global principle is now available for all actions that are equivariantly Z stable. So we can use this to deduce structural consequences of the actions. And for example, we have this new approach to classification that people are working on, and this, for example, this result of this list of people here. Carrion, Castillejos, Evington, Gapes, Schaffer, Lise, and White, that classifies uniform tracial closures based on their tracial state simplexes. And we can try to imitate this or bring this to the dynamical setting and use this to our advantage when we will actually try to classify the actions on the classifiable C-star algebras. Because in this new approach to classification is really like a two-step process, first focusing on what happens at the level of the traces and then trying to lift this to the general C-star algebraic statement, and this can be a tool in this. So this is what I want to talk about. Thank you for your attention.